In this example, we're going to introduce the idea of Rolle's theorem, which is really kind of a special case to the mean value theorem. So a real quick summary of the mean value theorem is that if we have 2 points, and it's going to start off with your graph has to be continuous and differentiable between these 2 points, right? So some sort of an interval has to be continuous and it has to be differentiable. And if that is the case, then if you were to find the slope of the endpoints, right, there is some point somewhere in between that has that same slope, the instantaneous slope. So Rolle's takes that same idea. It says if f of x is continuous and differentiable over that interval, but with when you plug in the a value, plug in the b value, they end up matching. So here's kind of my visual associated with it. If I plug in an a, I get this value. I plug in b, I get the exact same value. So as long as this graph is continuous and there's no abrupt changes in it, it's this nice smooth curve between these 2 points, something potentially like this is going to happen, right? Let me make that a little bit less flat. So let's see. Something like that happens, right? So the idea of a mean value theorem is that whatever that slope is between these two, there's going to be another point somewhere along the way that matches that slope. Well, if our slope here is 0, then that means somewhere along the way, we are going to have another slope at a particular point that is going to equal 0. And that's what this is saying, that somewhere we have a slope of 0, right? That's what a Rolle's theorem is. So it's basically a special case to a mean value theorem. Mean value theorem is, I don't know what that slope's going to equal, but here I know exactly what that slope's going to equal. It has to equal 0. So we're going to try to figure that out. So we're going to find an interval in which Rolle's theorem applies on this cubic function, and then find all points to where our slope does equal 0. So in order to figure out where Rolle's theorem applies, we have to basically, we're looking for when we have slopes of 0, right? But we don't know that until we figure out where we have some y values matching. Well, if I have an x to the third, I'm going to cheat this a little bit, we have this kind of a look to it most likely, right? So we could basically cut a line right through here, and these points right here are where the y values would match. So if I have to choose and I'm like, well, I don't know what to set this thing equal to, I'm going to try to set it equal to the easiest thing that I can, which is just going to set it equal to 0. So, which also means I would be trying to find x-intercepts. So real quick, before I jump into the math, let's make sure that this thing does have 3 x-intercepts, right? Can I actually set it equal to 0, or does this get a little bit more complicated? So if I look at Desmos, and I graph this equation, and here it is, and this is what it looks like. Beautiful, right? So I have these x-intercepts. So let me go back and start doing the math on this. Otherwise, if it didn't happen and this curve was up here, then maybe I'd have to set it equal to 10 or something else and then go about solving it. But I can just take this equation and set it equal to 0. So that's what we're going to do. So we're going to do x to the third minus 7x squared plus 10x. And we're going to set it equal to 0. I can take an x out of it, and that'll leave us with an x squared minus a 7x plus 10 equaling 0. And then I can factor this quadratic. This quadratic factors into x minus 5 and x minus 2. And then each of these are going to give us solutions of 0, 5, and 2. So if I draw a little bit more accurate graph, we're looking at 1, 2, 3, 4, 5. And I have x-intercepts here, here, and here. Okay, so I want to figure out, it does say find all points C where we're going to have a slope of 0. So basically between 0 and 5, oops, we must have at least one point where your slope, your f prime of x equals 0. Okay, so it's a guarantee, right? We're going to have one somewhere here. We're going to have somewhere here. So I know that between 0 and 5, that's going to happen. Let's figure out where it is. So that just means that we're going to take now the derivative of this equation. Right, so if we do the derivative of this equation, we're going to get a 3x squared minus a 14x plus 10. And then we'll take that equation and set it equal to 0. Minus 14x plus 10, set it equal to 0, and then we'll try to solve it. Bad news is it is not factorable. So these answers we get are not going to be nice values. That's okay. We have quadratic formula that we can plug that into. So I would be doing negative b, which is negative 14, plus or minus b squared. So negative 14 squared minus 4 times a, which is 3, times c, which is 10, divided by 2 times a. And if I plug that into a calculator, I should get values between 0 and 5. So that's what kind of double checks that we're doing everything correctly. So if I throw that all into the calculator, the two answers that I would get would be 0.88 and 3.79. Right, so those two values are wonderfully between 0 and 5. So that 0.88 would be somewhere around here. And then that 3.79 would be, somewhere around here, which also kind of agrees with what our graph, our total rough sketch looks like. So that's the idea of Rolle's theorem. It's basically a special case of mean value theorem. And rather than us setting our slope equation equal to some slope, we're going to take our slope equation and set it equal to a very particular slope. But we really kind of needed to validate that these situations occurred, that it was continuous, differentiable, and we have an interval where the y values match each other.